Hello everyone, welcome to the 32nd episode of the series. In this video, we'll learn about diagonalization. So far, we've learned about eigenbases, how to compute an eigenbasis for a given matrix A, and how to determine whether a matrix has an eigenbasis without explicitly computing it. So there is this idea that eigenbases simplify multiplication with the matrix because we can write any general vector as a linear combination of these eigenbases, and that allows us to simplify multiplication of the matrix and any vector. So this idea can be encoded into a special factorization of A called the diagonalization of A. And if it's not clear what I mean by that, it will be in a moment. So let S be an eigenbasis for an n by n matrix A, consisting of vectors v1 through vn. So v1 through vn are eigenvectors of A, and they form a basis of Rn. Now, because these vectors form a basis of Rn, their concatenation, which we're going to call P, is an invertible matrix. So if we take the product of A and B, it's going to be just the concatenation of the vectors AV1, AV2, so on till AVN. And this actually happens in general. If you multiply any two matrices, the resulting matrix is made up of these columns, where each column is the product of the matrix on the left and a column of the matrix on the right. Now, because each of these VIs are eigenvectors of A with eigenvalues, let's say lambda I, we get that AP is lambda 1 V1, lambda 2 V2, so on to lambda n Vn. But this matrix consisting of column vectors lambda 1 V1, lambda 2 V2, so on till lambda n Vn can also be written as a product of the matrix P, which is the matrix concatenation of the vectors v1 through vn, and a diagonal matrix consisting of diagonal entries lambda 1, lambda 2, and so on till lambda n. So we can write this matrix on the right as a product of P and this diagonal matrix D. So what we conclude from here is that AP is equal to PD, and because P is invertible, we can multiply by P inverse to the right on both sides, and that gives us this theorem. So the theorem says that if we have an eigenbasis for A, and lambda I denotes the eigenvalue corresponding to Vi, where Vi is one of the eigen vectors in the eigenbasis, then we can factor A and rewrite it as a product of P times D times P inverse, where P is the concatenation of the eigenbasis and D is the diagonal matrix with the eigenvalues lambda 1 through lambda n on the diagonal. Now, such a factorization is called a diagonalization of the matrix A, and therefore a matrix with an eigenbasis is called diagonalizable, because every time you have an eigenbasis, you can form the matrix P and the matrix D. Okay, so in this example, we just have two instances of diagonalization of a matrix A. So in both these instances, we've written them as a product of a matrix P, a matrix D, and a matrix P inverse. So we can actually read some information from here. So if you're given just this matrix A and this factorization, we can look at the middle matrix and say that, okay, the entries on the diagonal are 1 and 4. So 1 and 4 have to be the eigenvalues of this 2 by 2 matrix A. And if we look at P, we can conclude that the column vectors of P are going to be the eigenbasis for this matrix A. So the vectors -1, 1 and 1, 2 will form an eigenbasis for the matrix A. But there is one thing that we need to remember and be careful about, and that is the ordering of these eigenvectors and these eigenvalues. What I mean is both P and D depend on an ordering of these eigenvalues and eigenvectors, and it doesn't matter what order they're in, but they have to be in the same order. So they have to be matched up. So if you have um, 1 and 4 in that order, your eigenvector should be in the order of eigenvector of 1 and the eigenvector of 4. And when I say eigenvector, I'm referring to the basis element that you found in the computation of the basis of an eigenspace. Okay, so let's look at an exercise. We're given a 2 by 2 matrix with entries 2, 1, 1, and 2, and we just want to diagonalize it. That is, we want to write it as P times D times P inverse for some diagonal matrix D. So we're going to just write the key steps. I'm not going to go into the details because I believe you already are experts at this. So by the theorem that we just saw, we need the eigenvalues of A to form the diagonal matrix D and an eigenbasis to form the matrix P. So the first step would, of course, be to find the characteristic polynomial of A, and then factor it, and then set it equal to 0 to find eigenvalues. So my characteristic polynomial is x squared minus 4x plus 3, and that gives us eigenvalues 1 and 3. So there are going to be two eigenspaces, and we want bases for each of them. So, and we learned how to compute eigenspaces and bases corresponding to them using an algorithm introduced in the previous episode. So from the algorithm to compute the basis of a kernel in episode 28, we get the basis of the eigenspaces E1A and E3A. And then by taking these two vectors in these two sets and putting them together in a third set, we get an eigenbasis for matrix A. Now, once we have this eigenbasis, we get that D is the matrix 1, 0, 0, 3, and P is minus 1, 1, 1, 1. And once we have P and we know it's invertible, we can find P inverse. And once we have P inverse, we have the entire factorization. Okay, so let's move to an application of the diagonalization theorem. And this application allows us to compute exponents of a matrix A rather quickly. So if A is a matrix such that its diagonalization is given as B inverse for some diagonal matrix D, then for all powers n, A to the n is nothing but B times D to the n times B to the minus 1. And because D is diagonal, the entries of D to the n are the nth power of the entries of D. Because D is such a simple matrix, computing things at the level of D is very easy, and that is what makes this computation much faster. But why is this true? This is true because when you multiply A with itself, for example, you're going to get BDB inverse, BDB inverse, but the B inverse B in the middle is going to cancel to give you the identity, leaving a D squared in the middle, and so on. So let's look at an exercise. So we're given a matrix A and its diagonalization or its factorization into an invertible matrix P, a diagonal matrix consisting of its eigenvalues and the inverse of P. And we have to compute A squared using this factorization. So this is what I meant. Since A is B inverse, A squared, which by definition is the square of B inverse, can be written as this. Now the middle term cancels to gives you identity, and we get B times D squared B inverse. Since B was the diagonal matrix with entries 3, 2, and 1, D squared is going to be a diagonal matrix with entries 3 squared, 2 squared, and 1 squared. So now I mean, we already had our matrix B and B inverse, and we just computed our D squared. So A squared can be computed by taking the product of these three matrices. Now, this doesn't look as impressive, but wait till you have like a much higher power of A, like A to the 100 or A to a million. So instead of computing, A to the million by multiplying A to itself a million times, we can just compute D to the million very quickly, because it's just going to be the millionth power of each of the terms, and then multiply by P on the left and P inverse, or rather B on the left and B inverse on the right. Okay, now one of the most unexpected and powerful results in linear algebra is that an important class of matrices always has an eigenbasis. So there are two things here, an important class and something uh, called a nice eigenbasis. So let's look at the latter. Okay, so for that, we need a definition of an orthogonal set of vectors. So a set of vectors is called orthogonal if the dot product of any pair of vectors is zero. So in other words, you're taking any two vectors in that set of vectors, and if the angle between the two vectors is 90 degrees, that is, they're perpendicular to each other, then the two vectors are called orthogonal to each other. But when it happens for every pair of vectors in that set is called orthogonal. So the big result is that if A is a symmetric matrix, and that is our important class of matrices, then A has a basis of orthogonal eigenvectors. So not only A has an eigenbasis, the vectors in the eigenbasis are all orthogonal to each other. So this actually goes backward as well. That is, if A has an orthogonal eigenbasis, then A has to be symmetric. So this theorem and all of its generalizations are applied in a lot of different areas. Okay, so I want to end this episode with a small exercise. So we're given this 4x4 matrix, and we want to figure out whether this is diagonalizable or not. So because this matrix is symmetric, the spectral theorem tells us that it has a basis of orthogonal eigenvectors. That is, it has an orthogonal eigenbasis. And because it has an eigenbasis, it is indeed diagonalizable, because once you have an eigenbasis, you have information about eigenvectors and eigenvalues, and you can use those to create matrices P and D and P inverse. Okay, so with this, I would like to end this episode. Hopefully things made sense. I will see you guys soon. Till then, happy learning.